Welcome to our third video in this unit on complex numbers. In our last unit we took a look at cis theta and we investigated some of the rules for cis theta, and we're going to be expanding on those in this lesson. Hopefully you've had a chance to try it on your own. As the video indicated, you are to have tried this question. We're going to take it up right now and hopefully we got the same results. If you recall, in our previous video we talked about the rules for r cis theta in multiplication situation. We'll just go over this right here. Z squared would be r cis theta, of course, squared, which could be written as r cis theta times r cis theta. And so our rule from last time was if we got cis theta times cis theta, or cis alpha times cis beta, cis of A times cis of B, what we do is we add those angles together. So we get r times r, which is r squared, and then cis of theta plus theta, or in other words, r squared cis of 2 theta. So z squared is r squared cis of 2 theta. Let's check z cubed. Z cubed would be, and I'm just going to split it up into z squared times z. So z squared we've already shown is r squared cis of 2 theta, and we're going to multiply by r cis theta, and we get r squared times r squared is r cubed, and again we add the angles. So that gives us cis of 2 theta plus theta, or in other words, r cubed cis of 3 theta. After finishing z squared and z cubed, hopefully we've got z to the n here where we can see a trend. So z squared is r squared cis of 2 theta. Z cubed is r cubed of cis 3 theta. Hopefully you've been able to see the pattern. The nth exponent of z works out to be r to the n cis of n theta. So let's take a moment, break away from that what we just did on that warm-up, and talk about this guy, Abraham de Moivre. Alright, we'll just call him de Moivre. So why do we care about Abraham de Moivre? Well, in 1707 he was the first one to discover that which you just did in the warm-up. And there it is, looking all nice and warm and fuzzy on our screen. And it states that if you take the modulus of z times cis theta and you put it to the exponent of n, it can be simplified as the modulus of z to the n times cis n theta. Yes, that's right. We are going to prove this theorem using mathematical induction. So if you remember, with mathematical induction, we have to first prove it's true for n equals 1. So that would allow the first domino to fall. So let's make sure it does work for n equals 1. So if n equals 1, well, let's just split it into a left side and a right side approach. So on the left side, if n equals 1, we get the modulus of z, cis theta. And on the right side, we would get the modulus of z to the 1, to the exponent 1, cis 1 theta. So obviously that is the modulus of z, cis theta. So the first domino will fall. So let's now state what we are going to assume is true. And that is that we are going to assume true for n equals k. So that is that the modulus of z cis theta all to the exponent k is equal to the modulus of z to the k cis of k theta. Once we've stated that, we want to make sure we're focused on what we're going to prove true for n equals k plus 1. So we are going to prove that the modulus of z cis theta all to the exponent of k plus 1 will equal to the modulus of z to the k plus 1 cis of k plus 1 theta. So we've put the assumption and proof off to the side so that we can still see it, but it's not in our way. So let's finish off this proof. Let's start with the left-hand side of the proof statement. So that's the modulus of z cis theta all to the exponent of k plus 1. And we can break this up. Now remember, we are trying to use the assumption. In fact, we have to use the assumption in order to do a mathematical inductive proof. So we need to get the left side here involved somehow. So we can do that by breaking up the exponent k plus 1. So that would be the modulus of z cis theta. And we can multiply that by the modulus of z cis theta all to the k. So now we have our assumption. We can then replace or substitute this part of the assumption with this part. So let's do that. So that leaves us with the modulus of z cis theta times the modulus of z to the k cis k theta. That, when we multiply it out, multiply the modulus of z's together, so that's modulus of z to the k plus 1. And our rule for cis multiplication kicks in. That would be theta plus k theta. And all we have left to do is we look at the proof portion. What we're trying to get to is just to factor out a theta. And let's just reorder. When we factor out the theta, we got k plus 1 theta, which is what we're trying to prove. So therefore, it is true for n equals k plus 1. And then with authority, we can say, therefore, by mathematical induction, the result is true. So here's a good reason why we would want to use and know the Moivre's theorem. In this example here, we're asked to evaluate 1 minus I to the 11th. Well, similar to binomial theorem, the idea of doing this is not very attractive. It's got a lot of expanding to do, and we would have a whole bunch of terms. So remember, with binomial theorem, we would have 12 terms, and we'd have a lot of i's, and then we would have to simplify it down. But it becomes a lot easier when we use de Moivre's theorem. Now, in order to use de Moivre's theorem, of course, we have to be able to write this in terms of cis. So this becomes a good spot to review how to take a complex number and write it into polar form or cis theta form. So first of all, we have to find the modulus, and that would be the square root of the components here squared. So that would be 1 squared plus minus 1 squared, which is root 2. To find the argument, or the angle, we would use tangent of theta would be y over x, or negative 1 over 1. It's negative 1. So this angle is really a 45-degree angle, but let's just check out what quadrant it's in. So 1, negative 1 is down here in the fourth quadrant, and we know in the fourth quadrant that tangent is negative by the cast rule. So well, that would make that a minus 45-degree angle, or minus pi over 4. So 1 minus I can be written as root 2 cis of negative pi over 4. So rewritten, we can take 1 minus I to the 11th and now replace it with the 1 minus I with root 2 cis of negative pi over 4 and put that to 11th. And now is when we can use the Moivre's theorem. So that would put the modulus to the exponent of 11, so root 2 to the 11th, and then cis, and the 11 will multiply the angles, so that would become negative 11 pi over 4. Before I do anything else with that, I can simplify that negative 11 pi over 4. If you remember, one of the rules we have for cis, for polar form, is we can add multiples of 2k. So if I were to add a multiple of 2k, let's say 8 pi over 4, I would be at negative 3 pi over 4. Add 8 pi again, or 8 fourths pi again, I'd be at 5 fourths pi. So maybe I'll take that one. So root 2 to the 11th is cis of 5 pi over 4. So let's keep working with that cis. So let's keep the root 2 to the 11th outside. And a good review here again, cis is really cosine 5 pi over 4 plus I sine of 5 pi over 4. Now 5 pi over 4 is in the second quadrant, so cosine is negative, sine is positive, so we can rewrite that as root 2 to the 11th, and that would then become negative 1 over root 2, because it's a 45-degree triangle, plus I times 1 over root 2. You can see we've got a pair of root 2's on the bottom, close off that bracket, so I can multiply the root, take one of these root 2's here and multiply it out. So I would then get root 2 to the 10th times, that root 2 would be gone, negative 1 plus I. So root 2 to the 10th is really 2 to the 1/2 to the 10th, so that's 2 to the 5th times negative 1 plus I, which we can simplify as 32. So 32 times negative 1 is negative 32 plus 32I. And there's our final answer. This is the last question of this video, but I think it's a very interesting question. We're asked to develop a formula for cosine of 3 theta in terms of cosine theta. And you may be asking, how is this even related to what we're doing? Cosine of 3 theta, how are we going to generate that? Well, it does exist in the cis of 3 theta. How does it exist? Well, if we expand that out or write it in its full form, we get the cosine of 3 theta plus I sine of 3 theta. Now, at the same time, cis of 3 theta can be written as, using de Moivre's theorem, can be written as the cis of theta cubed. And we're going to work with this a little bit and expand it out. Remember, cis of theta is the cosine of theta plus I sine theta. And we're going to cube it out. Probably easiest to use binomial theorem to cube it out. That would work out to be cosine of theta cubed plus 3 cosine squared of theta, and then we would have an I and a sine theta, plus we would have a 3 cosine theta. We would get then I squared sine squared theta, and then our last term would be an I cubed sine cubed theta. So it would be 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Simplify it a bit, we would get a cosine cubed theta plus, this would be a 3 cosine squared theta sine theta, and that would be with an I. This term here, the I squared, would be going to negative 1, so that would actually be a minus 3 cosine theta sine squared theta. And then finally I cubed, which would be I squared times I, or a negative I, so that would be a negative sine cubed theta I. Bringing terms together, so if we took the real, these two are real numbers, that would give us cosine cubed theta minus 3 cosine theta sine squared theta. And the imaginary, if we pull out of these two an I, we would have a plus 3 cosine squared theta sine theta minus a sine cubed theta I. Now, isn't that very nice? But how does that help us in our question? Well, I'm just going to highlight this part here is cis of 3 theta, and this is also cis of 3 theta. So these guys should be equal. Cosine of 3 theta plus I sine of 3 theta should equal this whole part here. Or more importantly, cosine of 3 theta, as I highlighted, should equal the real portion of this version. Cosine 3 theta minus 3 cosine theta sine squared theta. And that's where we're now going to work. So this is where I am. I know that cosine of 3 theta is equal to cosine cubed theta minus 3 cosine theta sine squared theta. But the original question asks, as we go back to look at the top, to develop a formula for cosine 3 theta in terms of cosine theta. So not quite what I'm wanting. I need to remove this sine squared theta. So let's recall the Pythagorean identity. Sine squared theta is 1 minus cosine squared theta. So we're going to replace the sine squared theta with 1 minus cosine squared. So that becomes cosine cubed theta minus 3 cosine theta times 1 minus cosine squared theta. So let's expand that and simplify. So that would be cosine cubed theta minus 3 cosine theta plus 3 cosine cubed theta. These two will simplify, and our final answer is 4 cosine cubed theta minus 3 cosine theta. And that is the cosine of 3 theta. Now, before we leave this question completely, hopefully you could see a way that you could actually develop a formula for sine 3 theta in terms of sine theta. I'm going to leave that as a bit of a challenge for you to solve before you come to class tomorrow. So when you come into class, I want to take this one up, so hopefully you'll be prepared. So I'll just highlight these portions, sine of 3 theta, and we've got what's inside the brackets, because this is imaginary and so is this. So it's the imaginary portions that you can equate and solve in order to figure out sine 3 theta in terms of sine theta. Alright, class is over. Everybody out. Come on. Get out, keep going. Get out, get out, get out, get out. That's better.
De Moivre's theorem. De Moivre's theorem.
De Moivre. De Moivre.
This was a triumph. I'm making a note here, huge success. It's hard to overstate my success.